Continuing on with what happens when different stars die, let's take a look at what happens when the core of the star is above the Chandrasekhar limit. We get a supernova. Here we have a number of stars, and they are extraordinarily distant. They're actually in another galaxy. How do I know that? Because none of them have that plus sign. So they're going to be very faint. And all of a sudden, this star goes supernova. And this one supernova, this single star, is now brighter than all of these other stars put together. When a star explodes, the resulting expansion of all of the material from the star does take a while. This is actually over the course of about 10 years. So there's going to be something left over in the center, and all of this stuff is speeding out into space. It's going to be reused by another star, possibly formed into a planet where an alien could have some of these elements in their body. The Crab Nebula is a leftover remnant of a supernova from 1054. We've mentioned this before. There is a neutron star in the center of this, and all of this material is speeding outwards really, really fast to be used up by other stars. This was 1,000 years ago, and we can still see the remnants. So it's not like these things explode and then are immediately gone. There's a lot of material that gets blasted out. It takes a while for that to just diffuse out into the universe or to get reabsorbed in another star. What do you need to know about them? There are two main types. There's actually more, but we're going to focus on two. Please write these down. There's type 1a and there's type 2. Type 1a can only happen in a binary star system where one of the stars is a white dwarf and the other one is a red giant, which means they are very rare. It has to be a very specific setup to have a supernova type 1a. You have to have a white dwarf, you have to have a red giant, and they have to be orbiting each other. And we'll get to why in a second. Type 2, these are the ones that we've been talking about for quite a while. This is when a huge star just runs out of material in the core, doesn't have anything to push out because fusion turns off, and it collapses down and explodes. Type 2 is much more common. Type 1a, much more helpful for us. Let's take a look at these two. Starting with the one that's more rare but more helpful. This happens when you have a binary star system with a carbon-oxygen white dwarf orbiting around a red giant. What's happening is that white dwarf is stealing some of the outer layers of that red giant. That white dwarf is getting slowly bigger and bigger and bigger. Remember, we learned that stars are going to end as a white dwarf as long as the core is 1.4 solar masses and under. And it's that white dwarf that is the core. So every single white dwarf that exists is under 1.4 solar masses, because at 1.4, you now have enough pressure to do fusion, to do carbon fusion, and you would end as a supernova. So what's happening is this white dwarf is stealing material. It might be at 1 solar mass, and it's stealing material, and then it's now at 1.1 solar masses, and it's stealing more material. 1.2, stealing more material. 1.3, stealing more material. The second that it hits 1.4 solar masses, when it hits that Chandrasekhar limit, all of a sudden there's now enough gravity, enough pressure to do carbon fusion. Well, these white dwarfs are almost all carbon, which means the entire white dwarf fuses at once. The entire white dwarf immediately just fuses. That's a big boom. That is a 1A supernova. It basically turns the entire white dwarf into a nuclear bomb, where all of the carbon is going to fuse at once. Big supernova. Good timing. Very dramatic effect. Because this always happens at exactly 1.4 solar masses. It can't happen at 1.3, can't happen at 1.2. It never will get to 1.5. It always happens at exactly 1.4. Every single one of these type 1a supernova are exactly the same brightness. Every single one. You can't have a type 1a supernova that explodes at 1.3 solar masses. You can't have one that explodes at 1.5. It can only explode at 1.4. And because we know what's happening and how big that white dwarf is, we can calculate how much energy is coming out. It is 1 to 2 times 10 to the 44. That's 44 zeros. That is a lot of energy. That's a lot of joules coming out. And so we know exactly how bright every single type 1a supernova is. And because we know exactly how bright it is, just like with the Cepheid variable stars, where we know exactly how bright it is based on their brightness period, we now can calculate how far away these supernovas are by comparing it to how bright we see it in the night sky. Cool thing is that these are so bright, we can see them on the other side of the universe. You can't see an individual Cepheid variable star on the other side of the universe. But these supernova are so incredibly bright. Supernova are the biggest, brightest events in the universe. You can see these many billions of light years away. So when we want to know how far away something is on the other side of the universe, the only way that we have to do that is to look for these type 1a supernova. After these explode, absolutely nothing is left over. The entire white dwarf goes through fusion at once, and you do not have anything left over. There's no neutron star, there's no black hole, it's empty space. All of that material just flies out. There's nothing left over at the center. I want you guys to sketch this in your science journal. You have to have a binary star system where one is a white dwarf, one is a red giant, and they are close enough that the white dwarf can start to steal material from that red giant. When that white dwarf gets to the Chandrasekhar limit of 1.4 solar masses, the entire thing goes through fusion at once, basically exploding like a huge fusion bomb. A fusion bomb the size of a planet. There's nothing left over, and this red dwarf, if it's not completely blown apart, is slingshotted out in its headed in a new direction. Let's watch an artist's rendition of what's happening. You have a white dwarf. It is stealing material from this red giant, slowly getting bigger and bigger. When it finally gets to the Chandrasekhar limit of 1.4 solar masses, you have enough gravity to cause carbon fusion. Because it's mostly made out of carbon, the entire thing fuses at once, exploding in a 1A supernova. Nothing's left over. You eject that red giant star somewhere else, and you are left with this nebula of expanding, this planetary nebula of just expanding material. How can we use these to determine distances? The reason is that every single supernova is the exact same brightness, and every single supernova has the same light curve. In fact, it looks like this, what you see on your screen right now. Let's just pick a random supernova. They're usually named after the date that they were discovered. Let's choose 1999. And the absolute magnitude, we know how bright it should be if it was 10 parsecs away, is negative 19.5, much brighter than any star. So what we do is we take this supernova and we match it up to what we know it should be. That apparent magnitude is how bright we see it. So the apparent magnitude will actually change as we move this around, but when we match it up, we know that it should be this bright. We see it as this bright. Let's figure out how we calculate this. Little m is the apparent magnitude, so we type in 14.9. Big M is going to be the absolute magnitude, so we type in negative 19.5. This will calculate that this supernova is 75 megaparsecs away, which is 250 million light years away. Much farther than we'd ever be able to see a Cepheid variable star. So if this supernova happened in a distant galaxy, which it did, we now know how far away that galaxy is. Let's try a different one. Let's try 1994. and it matches there. 19.5 will stay the same. Let's change this to 13.9. This one was 47 megaparsecs away. And let's try 1998. You can see that they all match this light curve exactly. So this one was supposed to be negative 19.5 in magnitude. It was only 12.2. So let's put in 12.2. This one was only 22 megaparsecs away. I'm able to find the distance to these supernova in a mere matter of seconds. So all you need to do is find the absolute brightness of these supernovas. In this case, 1993. Let's do one more. Was 10.7. This one was only 11 megaparsecs away. Once you find how bright we see these supernovas as, you match up the light curve, and you can calculate the distance in less than a second. And this is the only way that we have to find the distances to things across the universe. The problem is that these are very rare. You'll see there's not a lot of these. Very rare, but very useful when they do happen. So let's move to type 2 supernovas. These are the ones that you've heard of. I'd say almost every star out there is going to just turn into a white dwarf. They're not big enough to go supernova. Only the biggest, maybe 5-10%, have enough gravity to cause a supernova to happening. Before we go farther, what's happening in the core is you actually do have hydrogen fusion happening, and then you have a little bit farther down where there's more pressure, helium fusion happening. A little bit farther down you have carbon and then neon, oxygen, silicon, and right at the very center, when you run out of silicon, now you start trying to fuse iron. And when you do that, you actually are absorbing energy instead of giving out energy. Because gravity is pushing in, the iron is absorbing energy, the entire core is going to collapse in a fraction of a second. This core is huge. It's many times bigger than planet Earth. And it collapses down in just a few seconds, which means the speeds that the outer layers reach are a significant fraction the speed of light. This material is going extraordinarily fast. If you are a star that is about 8 times more massive than our sun, which means your core is going to be 1.4 times more massive than the sun. And when your core runs out of fuel and starts trying to fuse iron, you basically have the entire core collapse extraordinarily fast. It collapses down until you get what's known as neutron degeneracy pressure. We talked about electron degeneracy pressure, where gravity is going to push all the electrons down to the ground state and then push all those atoms together. So the only thing pushing back out are the electrons against the other electrons. If you have more than 1.4 solar masses, what happens is it actually has enough gravity to take those electrons and push them into the nucleus of the atom. If you take an electron and push it into a proton, you have a negative and a positive. They cancel out. You turn that proton into a neutron. You now don't have any electrons pushing out because they've all been pushed into the protons, and you can get that material much, much closer together. You take all of this material, which is about the size of the planet, you push it all much, much closer together, and you are left with a pile of neutrons condensed down to roughly the size of maybe Manhattan. These neutrons are super compressed together into a very dense core, basically an atomic nucleus. And why do the neutrons not collapse down into themselves? There's this thing in quantum physics called the Pauli exclusion principle, which says that two pieces of matter can't occupy the same part of the universe. They have to be excluded from one another. You can't have one neutron be in the same location as another neutron. And that is the only thing keeping gravity from winning. It's basically like taking a bunch of billiard balls and trying to, with your hands, squeeze them into each other. You can't do it. Gravity is not strong enough to take a neutron and squeeze it into another neutron. The Pauli exclusion principle tells us that that can't happen. That's just part of quantum physics. So you have this ball of neutrons that can't get any smaller. We call that neutron degeneracy pressure because this has now degenerated, so the only thing pushing back out against gravity is the fact that neutrons can't be in the same space. You now have an atomic core the size of a city, made up of neutrons pushing back against gravity. And what happens, all of this material is going to fall down until it hits that core of neutrons, and it's going to rebound. But this material is going at a significant fraction the speed of light. Imagine taking a basketball and slamming it into the ground at like 10% the speed of light. It would rebound really high up in the air. It would pop, but if it didn't pop, it would rebound extraordinarily high. That's what happens with the star. The core collapses on itself extraordinarily fast, hits this ball of neutron degenerate matter, bounces off, and that shock wave then travels outwards through the star and blows the outer layers apart. Keep in mind, these are red supergiants, so this is many millions of miles across. And in about an hour, that shock wave is going to reach the outer layers of the star, and it's a big boom. It's a huge explosion. It completely obliterates those outer layers, shooting them off into space. So in order, it goes like this. You have this onion layered type of core where you have hydrogen fusion, and then helium fusion, and then carbon fusion, oxygen, silicon, until you get to iron. And when you start trying to fuse iron, you absorb energy. And all of a sudden, not only is gravity winning, the iron is absorbing energy, and the inner core starts to collapse at extremely fast speeds. The outer layers then also collapse down until you take those electrons, pushing them into the protons, creating this neutron degenerate matter. You can't get them any closer together because of the Pauli exclusion principle, and so that material is then going to bounce or rebound back out through the outer layers of the star. This shock wave, when it reaches the surface, is going to completely obliterate the star in a huge, giant supernova explosion. The outer layers are gone. The only thing that remains is that ball of neutron degenerate matter at the very center that everything bounced off of. Go ahead and sketch this, just like you sketched what a type 1a was. This is a supernova type 2. This is the best computer-generated animation that I could find of a supernova happening. You have a red giant star, and if you cut away and go down into the core, you'll see that there's hydrogen fusion and helium fusion, but at the very, very, very center of that core starts trying to fuse iron. You can't fuse iron and push out. You're going to basically absorb energy, and everything collapses down, creating that neutron degenerate matter. It rebounds back out, creating a supernova explosion. What's left over is a planetary nebula, and at the very center, that big ball of neutrons that everything bounced off of. I've mentioned supernova 1054, so I'm not going to spend a lot of time on that. That's the one that was recorded around the world, except for in Northern Europe. It left the Crab Nebula. At the center is a neutron star. A lot of people want to know, though, when is the next star going to go supernova?
At an estimated 640 light years away, there is a star so big that if it was at the centre of our solar system, it would consume the orbits of Mercury, Venus, Earth, Mars, and possibly even Jupiter. This gigantic star can be located in the constellation of Orion. It is one of the 10 brightest stars in the night sky, and its name is Betelgeuse. Also known as Alpha Orionis, Betelgeuse is a huge red supergiant star that fluctuates in size from between 700 and 1000 times the diameter of the Sun, making it one of the largest known stars in the Milky Way galaxy. Betelgeuse is about 10,000 times brighter in visible light, but if the human eye could view all the wavelengths of radiation, it would be the brightest star in the night sky. The reason for its variable size and brightness is because the colossal star is nearing the end of its life cycle. At 10 million years of age, it is already an old supergiant star. Betelgeuse would have burnt through its hydrogen relatively quickly, reducing its lifespan considerably compared to smaller stars such as the Sun, which is expected to exist for about 6 billion more years. What makes this distant star so special from our perspective, however, is that within the next million years or so, Betelgeuse will explode in a magnificent supernova that will be visible from Earth. As a red supergiant, Betelgeuse's innermost region will be fusing heavier and heavier elements until its core is so heavy it cannot withstand its own gravitational force. During these final moments, the colossal star's core will collapse in on itself and cause a giant explosion. After an initial brief flash, Betelgeuse will increasingly grow in luminosity over a period of weeks, becoming billions of times more brighter than the Sun. From Earth, the explosion may be as bright as the Moon and could potentially still be visible during the day. It may also last for a couple of weeks or even months, eventually fading away into the darkness of space. Because Betelgeuse is estimated to be 640 light-years away, it does mean that the bright star may have already gone supernova at any time from the 14th century onwards.
There are a number of candidates. All of them are red giants or red supergiants. UI Scuti, Betelgeuse, BY Canis Majoris, all of those are going to go supernova. However, those are all far enough away that they're not going to affect us. They're not going to hit us with a shock wave. They're not going to give us deadly ionizing radiation. The closest one to us is IK Pegasi. It's about 150 light years away, and that's actually going to be a type 1a supernova. So that's a binary star system with a white dwarf stealing material from a red giant. Right now it's about 1.1 times the mass of the Sun, and it has to get up to 1.4. That's not going to happen for a couple million more years. So it's not like we need to worry about anything going supernova around us anytime soon and affecting us. Even when this one does go supernova, it's going to be really bright, but it won't kill off all of the life on Earth. One last review of the difference between 1A and type 2. If this seems repetitive, it's because you need to know it.
So now you know the difference between a type 1A and a type 2. A type 1A is where a white dwarf at the exact mass of 1.4 times the mass of the Sun implodes in on itself as it exceeds the ability for electron degeneracy to hold back that carbon ball. In the case of a type 2, it's an enormously large star at the end of its red giant stage where the core begins to form iron. Once it forms iron, it can no longer generate the heat to keep the core up. The core builds up to the point where electron degeneracy can no longer hold back the weight of the core. The core collapses in on itself in a fraction of a second, builds up to tremendous high temperatures, tremendous amount of neutrons are generated, they push out very fast, bounce into the material, very dense material around that iron core, heat it up to tremendously high temperatures, and cause the core to, the rest of the star to explode. It's that last remnant, that core of the star at the very center, which is now a big ball of neutrons, that will remain. And so at the end of a type 2 supernova, the very center of it will simply be a big ball of well, not a big ball, but a tremendously dense ball, primarily of neutrons.
What's left over after a supernova? Well, first you have to have a huge star, so like 8 to 10 times the mass of the Sun, so that the core is 1.4 solar masses or more. Afterwards, you can have three possibilities. You could have nothing, neutron stars, or black holes. We're going to get to black holes tomorrow because those break science. So let's talk about the first two. Nothing left. That happens with a supernova type 1A. And there's a picture of it. Neutron stars. A neutron star is that degenerate matter where it's basically a bunch of neutrons the size of a city. You have an atomic nucleus the size of a city. It's what everything bounced off of during that supernova explosion. The density of these is about the most dense thing that we can possibly even imagine. In fact, it's hard to even know what's happening at the core of these because the we have no clue. We can't recreate that on Earth, and it's really dense. Neutron stars also are going to emit a lot of radiation, and they spin because the star itself was spinning, so they continue that angular momentum. A neutron star is going to spin, sometimes many, many, many times a second. And as we see that, it looks like a lighthouse to us. We call that a pulsar. The fastest one is 642 rotations per second. And that rotation doesn't change. It is very stable. So the amount that it's rotating, you can set your clock by it. If it rotates every 642 times a second, it's going to do that every single second for millions, if not billions of years. And every time we see one of these supernova remnants, you're going to either have a black hole or a little neutron star at the center. Let's take a look at these a little bit more in depth, because these hurt your brain to try to understand.
Neutron stars are one of the most extreme things in the universe. They're like giant atom cores, kilometers in diameter, unbelievably dense and violent. But how can something like this even exist? The life of a star is dominated by two forces being in balance: its own gravity and the radiation pressure of its fusion reaction. In the core of stars, hydrogen is fused into helium. Eventually, the hydrogen in the core is exhausted. If the star is massive enough, helium is now fused into carbon. The cores of these massive stars become layered like onions as heavier and heavier atomic nuclei build up at the center. Carbon is fused into neon, which leads to oxygen, which leads to silicon. Eventually, the fusion reaction hits iron, which cannot fuse into another element. When the fusion stops, the radiation pressure drops rapidly. The star is no longer in balance, and if its core mass exceeds about 1.4 solar masses, a catastrophic collapse takes place. The outer part of the core reaches velocities of up to 70,000 kilometers a second as it collapses towards the center of the star. Now, only the fundamental forces inside an atom are left to fight the gravitational collapse. The quantum mechanical repulsion of electrons is overcome, and electrons and protons fuse into neutrons packed as densely as an atomic nucleus. The outer layers of the star are catapulted into space in a violent supernova explosion. So, now we have a neutron star. Its mass is between 1 and 3 suns, but compressed to an object about 25 kilometers wide, and 500,000 times the mass of Earth in this tiny ball that's roughly the diameter of Manhattan. It's so dense that 1 cubic centimeter of neutron star contains the same mass as an iron cube 700 meters across. That's roughly 1 billion tons, as massive as Mount Everest, in a space the size of a sugar cube. Neutron star gravity is pretty impressive too. If you were to drop an object from 1 meter over the surface, it would hit the star in 1 microsecond and accelerate up to 7.2 million kilometers per hour. The surface is super flat, with irregularities of 5 millimeters maximum, with a super thin atmosphere of hot plasma. The surface temperature is about 1 million Kelvin, compared to 5,800 Kelvin for our Sun. Let's look inside the neutron star. The crust is extremely hard and is most likely made of an iron atom nuclei lattice with a sea of electrons flowing through them. The closer we get to the core, the more neutrons and fewer protons we see, until there's just an incredibly dense soup of indistinguishable neutrons. The cores of neutron stars are very, very weird. We're not sure what their properties are, but our closest guess is superfluid neutron degenerate matter or some kind of ultra-dense quark matter called quark-gluon plasma that doesn't make any sense in the traditional way and can only exist in such an ultra-extreme environment. In many ways, a neutron star is similar to a giant atom core. The most important difference is that atom cores are held together by strong interaction and neutron stars by gravity. As if all this wasn't extreme enough, let's take a look at a few other properties. Neutron stars spin very, very fast, young ones several times per second. And if there's a poor star nearby to feed the neutron star, it can rotate up to several hundred times per second. Like the object PSR J17482446 AD. It spins at approximately 252 million kilometers per hour. This is so fast that the star has a rather strange shape. We call these objects pulsars because they emit a strong radio signal. And the magnetic field of a neutron star is roughly 1 trillion times stronger than the magnetic field of Earth, so strong that atoms get bent when they enter its influence. Okay, I think we got the point across. Neutron stars are some of the most extreme, but also some of the coolest objects in the universe. Hopefully, we'll one day send spaceships to learn more about them and take some neat pictures. But we shouldn't get too close.
That's a big boom. And a big boom.